Physical Chemistry, Chapter 18, Section 1. We're starting quantum mechanics now. We're first going to talk about blackbody radiation and energy quantization. This is the beginning of quantum mechanics. Now, before 1900, the year obviously, there was classical mechanics. Now, with classical physics. There's classical mechanics such as Newton's laws of motion. There's the Maxwell theory of electricity. There was magnetism. There was thermodynamics. And there was the kinetic theory of gases, like the G function, Maxwell distribution. But this gives incorrect values for the molar heat capacity constant volume for polyatomic molecules, such as carbon dioxide. So that was one failure of quantum mechanics. Blackbody radiation was the second failure of classical mechanics. For example, let's say we have hot iron glowing red because it's so hot. So here is R, the radiation, I guess, a function of nu. So here's nu, so it's like wavelength, frequency. Okay, so this is the distribution function. So Rayleigh-Jean, they predicted that by classical mechanics, that as frequency went up, that it should just go up higher and higher and higher and higher with no limit. But instead what we see at like 500 Kelvin, we get a curve that looks like this. And then at 2000 Kelvin, we get a curve that looks like this. So nu is frequency, so this is increasing frequency. That'd be like, red, green, blue. Or, infrared, visible, ultraviolet, whatever. So RV, this function, it's the rate of emitted radiation divided by the surface area, the unit surface area. So R is our distribution function. So what we see is that at higher temperature, the peak shifts to higher frequency. So we get the frequency is equal to the speed of light, celeritis, divided by lambda, the wavelength. So 1900 we had Rayleigh-Jean's. Based on classical physics and the equipartition of energy, you would expect it to keep going up higher and higher and higher, but goes to infinity in the ultraviolet region. This is called the ultraviolet catastrophe. So this function, R of nu, frequency, is equal to 2 pi kt divided by the speed of light squared times nu squared. See how it would keep going higher and higher and higher as a parabola. And then of course k is Boltzmann's constant. And this would basically go super high in the ultraviolet range. But here's what happens. A black body absorbs all wavelengths. Therefore, when you heat it up, it emits all wavelengths. So let's say you heat up iron. If you heat it up just a little bit, it turns red. If you've ever done cooking on an old-fashioned oven, you know this. But then it gets hotter, it turns orange. And then it gets even hotter, it'll turn yellow-white. And then if it gets really, really hot, it'll turn blue-white. So to learn about this, you can run the applet called My Black Body. So here's another graph, same idea. Frequency on the horizontal axis. This function on the vertical axis. And again, so here we have the units though. 10 watts per square meter per second. That's weird. Okay, so you see 500 kelvins, the peak is over here. 1500 kelvins, the peak is over here. 2000 kelvins, the peak is over here. So the peak is shifting towards higher frequency, but the peaks are also getting taller. Okay, so this is what a black body might look like. You have some sort of hollow cavity. It's all bumpy inside. So light comes in, it bounces around, it never gets reflected back. So it gets completely absorbed. So light bounces around inside and it gets absorbed entirely. Since the cavity is a perfect absorber, it's a perfect emitter too. And then this function is emitting radiation. It's emitted, how much emitted radiation there is per surface area. Now by classical physics, there should be no such thing as darkness. Even if room temperature based on this, everything should be glowing, not just in visible light, but even in ultraviolet light. Because based on the equipartition of energy, again we get this R of frequency is equal to 2 pi kt over c squared times the frequency. There's So it is temperature dependent, but even at room temperature, you would expect stuff to be glowing. And again, K is Boltzmann's constant. And again, this formula is what leads to the ultraviolet catastrophe. Okay, so now we're going to talk about the quantum mechanics instead. So Planck did this by hand, by trial and error. So what he ended up with, R nu is equal to A nu cubed divided by E to the B nu over T minus 1. This was in October of 1900. So it turns out this constant A is equal to 2 pi h over c squared, and B is equal to h over k. And again, K is the Boltzmann constant. So we get R of nu is equal to 2 pi h over c squared times nu cubed over E h nu over kt minus 1. So this is actually where Planck's constant comes from. So the derivation of this depends on some important assumptions. So Planck's assumption was that energy could be added or subtracted to these oscillators only in packets, quanta, of size h nu. So these oscillators, they're vibrating atoms, or actually vibrating charge. Now heat makes atoms vibrate. Now Planck called them oscillators. He said that energy wouldn't concentrate in high oscillators. So this is why we hardly get high frequencies of energy, light, like visible light and ultraviolet. Now energy doesn't just concentrate in one atom. The high energy oscillators, they don't vibrate. It's very improbable since energy is dispersed among oscillators. So we have Wien's law. I'm not sure the pronunciation, but anyway, I'll call it Wien's law for now. So we get the maximum frequency, wavelength is times temperature is equal to constant. And that's 2.898 times 10 to the negative third Kelvin meters. K is kelvins, M is meters, obviously. And then the Stefan-Boltzmann law is that power is proportional to this, what is that symbol? Is that a delta or sigma? Times temperature to the fourth power. And then this symbol here is equal to 56.4 nanowatts per meter squared per Kelvin to the fourth. So lowercase n, capital W. Actually, I think it's lowercase w. But anyways, nanowatt, and then K is kelvins, of course. So here's another way of putting it. In classical physics, you have different energy levels. And you can have any energy level. This is supposed to be completely shaded in. It's a continuum. But according to quantum mechanics, or at least based on Planck's model, you have the lowest energy, energy naught, and then the next higher energy, energy 1, 2, 3. Now this is shown evenly spaced out. That's because remember he said they could only be amounts in h nu. So only certain energy levels are allowed. You have these lines that are not a continuum.